Okay. So is it recording? Yes, it's recording. So in kinetic model of matter, obviously, I guess you might have thought about this correctly. So you'll talk about solids, right? We talk about the states of matter. Let me keep it generic, right? You talk about the states of matter, right? Talk about the states of matter, okay? And that are what? That are three states of matter: solids, liquids, and gases, right? So since we have these three states, so we will have these basically solids have different properties, and we'll talk about liquids and gaseous properties and what are the characteristic definitions of these particles. How is the kinetic model of matter for solids? How are they arranged? What is the spacing? Can they be compressed? And so on and so forth, right? So, and then we will talk about some laws, right? Some relations, right? Some relations, which will include what? Which will include Boyle's law, right? It will include Boyle's law. It will include Boyle's law. It will include Charles' law. They will, I guess you might remember these names, right? We will just talk about this in detail in a while. Don't worry. We talk about pressure law. Okay. We talk about pressure law. Okay. And then we talk about, and I guess this is it. And then combine them together, all of them together. That is called the combined version, right? The combined version of these laws. Okay, and we'll solve some questions in the slides, which will make sense, right? So this is just the first part, that is states of matter, is going to relate some of the chemistry lectures. The rest of the part, it will be basically all physics, right? Okay, so let's start. States of matter, right? First of all, what is matter, right? So you might think about this question first. What is matter, right? So I guess we talked about this in the start, right? Matter. In your first chapter of chemistry, you talk about this. What is matter, right? So matter is basically everything is made up of matter, right? What is matter? Okay, so the definition is that everything is made up of matter. Everything is made up of matter. Made up of matter, right? And but what is matter, right? So matter is basically what can be everything which we have studied, right? Which study in the chemistry. That is atoms. It can be atoms. It can be ions, right? It can be compounds. It can be molecules, and so on and so forth, right? So on and so forth, etc. Right? So this is the definition which is written over here, that matter is made up of tiny particles. Particles can contain either atoms, molecules, ions, electrons, right? Which are too small for us to see directly, right? So we cannot see them by our naked eyes, right? So, but they can be seen by scientific eye, right? So, what do you mean by scientific eyes? Eyes means obviously microscopes, right? We have microscopes in our labs, so you can use microscopes and observe. You can say how is an atom arranged. In an atom, how is the electron and the nucleus arranged over there, right? So, this is again just defining what is matter and how can we observe it, right? So, we have a demonstration over here on the bottom right. So, it is a protein particle over here, right? So we have used the electron microscope over here. This is figure 2.1.1, and this is a molecule of a protein, right? So you can see that if you just zoom in over here, if I just zoom in over here, you can see, if I just zoom in over here, okay, if I just zoom in, let me just zoom in here. Okay, you can see it's a zoomed in version of a particle, and obviously you cannot see it by naked eye, right? Has been it has to be basically sub microscope, so it has been observed under a microscope, and you can see that you can see some sort of concentrated part over here, which is called the nucleus, and you can see some shells over here, right? It can be basically electrons, right? So these are, you can see different, they are different shapes, okay, because molecules can contain different particles combined together, right? Okay, it can be diatomic, triatomic, or different, let's say, different particles together, right? So protein has different atoms combined together. You can study the structure of protein, and it will make sense in a while, right? Okay, so again, they are saying a molecule can even contain smaller particles called atoms, as I told you guys, and they are in continuous motion, right? So, acha, this is an important interesting point over here, right? That everything is in continuous motion. Okay, everything is in continuous motion. So, if you just zoom in into your hand, right? Let's say this is Hamza, right? This is Hamza over here, and Hamza wants to use the microscope and wants to see his hand, right? Hamza wants to see his hand, right? And he uses a microscope. Okay. So if you use a microscope over here, he will see what? He will see a zoomed in version over here where you will see atoms, right? Atoms like these, right? Atoms like these. And they are continuously vibrating, right? They are continuously vibrating. Okay. So any living particle will continuously vibrate. Okay. Only if it is dead, then it stops the motion, right? But atoms continuously keep on vibrating. So, yeah. So if I just I can just take the example to the universe entirely is vibrating, right? See, because everything is constant motion, okay? Nothing is stopping. Okay. So this is just an introduction about the chapter over here, that what are matters and what is the states of matter, right? So states, obviously state means what? State means K. At a particular time, the atoms arrangement are arranged in what manner, right? So it can be either in a solid state, it can be in a liquid state, right? Or it can be in a gaseous state, right? So these are the states, right? And we have studied what is matter now. So we will combine these together and in a single thing together to basically study different states and their properties in detail, right? Okay, so let's continue. So properties of solids, liquids, and gases, right? So these are very important over here. आपके पास एग्जाम में सीधा क्वेश्चन आता है, right? कि properties of solids बताएं, ठीक है? So you can give 2 marks, 3 marks. So you should know at least three properties of every state, right? So it is pretty straightforward, right? So how do I draw a solid? Okay, let me draw a solid over here. Let me just do into shape. Okay, so let me just draw a square. Okay, it's a square. It's not a square. It's not changing into a square. Okay. Okay, so let me just fix it again. Square. Okay, not drawing it. Let me leave this point. Okay, let me just draw a cube over here, right? So let's say it's a cube over here, right? It's a cube over here, okay? And solid, right? In solid, how are the particle arranged? Let me just draw the particles over here. So it's like these, right? It's like these compressed together, right? Let me just draw the particles. It's a three-dimensional picture. I should have drawn two-dimensional, right? To just save time. Okay. Okay, so yes. Right? The particles pretty close together, right? You can see in a solid, let's say it's an ice cube, right? Let's say it's an ice cube. So you have an ice cube in front of you. And just go to your freezer and take an ice cube and just study this, right? You will find out what the following things, right, which is written over here. So the solids have fixed definite shape, right? They have fixed volume, okay? And they're not compressible, right? So let me just write down the properties of it. See, what are the properties of solids? The properties of solids are as follows, right? Okay, they have fixed shape, they have fixed shape, right? And they have fixed volume, right? They have fixed volume, right? Why do they have fixed volume? Because the particles pretty close together, they don't have enough spaces, so they cannot move away. They cannot move to and fro, right? So they are stuck together in a fixed shape, right? If they have a fixed shape, they have a fixed volume, right? Okay. And what is the third property? Okay, that it is incompressible, right? What is incompressible means कि since there are no spaces between the atoms over here, they cannot be further compressed, right? So if they don't have spaces, how can the atoms overlap with each other, right? So they are incompressible, right? Okay, and these are the properties over here, right? So again, they are in a fixed shape, they have fixed volume, okay, and they are pretty close together over here, right? So when a force is applied to a solid, atoms move slightly further apart in the direction of the force and stretching reverse, right? When a solid is heated, so the distance between the atoms increases. If enough energy is applied to solids, they basically move further apart, right? So they're just explaining the basically process of melting over here, right? So let me just dictate this in a different slide. Let's say you have an ice, right? Let's say you have an ice cube, right? Let's say you have an ice cube. Let's say you have an ice cube over here, right? Let me just draw the ice cube structure. Okay, and you have this, right? Let's say if you heat it, right? What happens after heating it? You convert to liquid, right? Convert to liquid, like it converts to liquid. So what is happening over here, right? So what is happening over here? So we are providing basically force, right? Because we're providing heat, right? What does heating does? Heating basically causes the particles to vibrate, right? The particles inside the solid structure starts to vibrate. Okay, vibrate vigorously. Vigorously means strongly, right? And if they vibrate, okay, they will basically push each other apart. Okay, if they have enough energy, so the particles basically moves further apart. Particles moves further apart, right? And if they have moved further apart, they have now small spacing that is greater than the spacing in solids. So the particles are arranged like these. Okay, now they have spacing, right? So now they basically change state. It has changed the state, right? So what is basically melting over here? So we have one change of state over here, right? So we have the first change of state over here that is called melting, right? So what is melting? Okay, so the state, when the state, when the state changes from solid to liquid, solid to liquid, okay? So it is called melting, right? It is called melting, right? So this is the definition. This is the first change of state which you have in your sort of dictionary right now. Take it. It's called melting. Let me just fix my G. It's on pretty messy style. Okay, so it's called melting. And then we have further smaller point over here that is called melting point, right? So because we also have a melting point over here, right? We should also know what is melting point. It is very simple, right? It is very simple over here. It is just as follows, right? So the point, the point at which the solid starts to convert to liquid, right? It is the point at which the melting process starts, so that is called melting point, right? It's pretty simple, right? So this is the first the change of state you have in your syllabus, right? So I hope it is simple. If you have any questions, you can just write down in your piece of paper. So I would suggest you should have a copy and a pencil in your hand right now when you're watching the recording. If you have any questions, write it down and send it into the group, right? As a PDF, not a picture, right? And you can tag the teacher assistant TAS man, because it will take time for me to respond, because right I might not have internet access when I'm in Masjid al Haram, right? So please try to use your TA, right? Okay. Now we have liquids, right? So now आपके पास सॉलिड आ चुके थे, आपने उसकी प्रॉपर्टीज पढ़ ली हैं, आपने उसके स्ट्रक्चर पढ़ ली हैं, देन आपने उसकी we have also studied the first change of state, right? That is called melting. Okay. Now, like in the next stage, we have liquids over here, right? So, what are liquids? Let me just draw a container. Okay. Let me just draw a container. Let me just draw a container like this. Okay. And it has liquid, right? It has a liquid over here inside it, right? It has a liquid. And you can see the particles inside this. If I just, let's say, if I just zoom in into this part, the particle would be as follows, right? And this is the liquid. Let me just draw the liquid color over here. And I just want to show you the particles arrangement over here, right? The particles would be arranged like these. Okay? Will have spacing which are greater than liquid, right? And they are, since they are free to move. Okay. So again, if you can put the liquid in, let's say, in this shaped container, so it will take the shape of this container. Okay. If you put it in this, let's say, in this shape of a container, so it will take its this shape. Okay. So you can now start to think about what are the properties of solids, liquid, sorry. Okay. So these properties basically dictate what processes can they go through, right? Liquids basically are used as lubricants, right? They are used for combustion, right? They are used for cooling. Okay, they are used for, let's say, producing electricity, right? And different states had different utilities, right? The first property of this particular state is they have no fixed shape, right? They have no fixed shape. They have no fixed shape, but they have fixed volume, right? They have fixed volume, by the way, right? Okay, why do they have fixed volume? Let's say if I pour this liquid over here or over here, the volume would remain same, right? Because the particles are not so far away that they can get lost. They are contained in the fixed in this particular liquid. So particles cannot escape the boundaries of the liquid, right? They remain intact. They have fixed volume, right? And the last one is K. They are compressible, but rarely. Yeah, again, let's keep it simple. They are incompressible, right? So in your syllabus, it's stated directly that they are incompressible. Again, they are incompressible because again, if you try to squash the liquid, the spacing will reduce, but again, that not much. Okay, but not that much, right? So again, let's go through what is written into your textbook. What are they saying, right? So they had definite volume, but their fixed their shape depends upon the container they kept in, so they have no fixed shape. CK, they are more easily compressed or stretched than solids and also expand when heat is supplied, right? So again, this point is a little doubty over here, right? Because this cannot be compressed like a gas, okay? Because it has enough spacing, which is greater than solids. You can see now. Solids, we have no spacing at all, right? But liquid, we have spacing. So it's basically thought of this. They're compressible, but not greater than not greater than gases, right? So it's pretty, if you compress a liquid, you can try it. You can try it out in your homes, right? Let's say try to squash a liquid, right? Like you can have a small container and you can just use a sort of a sponge over here, right? You can have a small container like a glass, right? You can just pour some liquid over here. You use a sponge, right? Sponge. And you can just try to squash it, right? Try to squash it. You will see basically it will not compress that much, right? It will basically break the glass. The container is not so strong. Okay. So yeah, it is a debatable point over here. So you can just use this definition, right? Okay. Okay. The particles of liquids are further apart, which we have seen. Okay, we have seen this in the from the structure, right? And they have a less order. Obviously, they're not ordered. They can move to and fro. They're not fixed in position, right? They can slide over each other. And when liquid is poured, the liquid then takes on the shape of the new container, right? So again, it has no fixed shape. It has but fixed volume, but it is compressible, but not greater than gas, right? So these are the properties of liquid, right? Which you should keep in your head, right? Whenever this question appears in your exam, it should be on your fingertips, right? So there can be MCQs which can basically ask you to separate out, identify an atom. Let's say they have stated the properties. वो आपको पूछें कि बताएं ये liquid है, solid है या फिर gas है, depending upon the property, right? So be aware about that. Okay. Now we have some change of states over here, right? So let me just dictate the state over here on a new slide. You can read this on your own. So we have again the second change of state that is called freezing, right? Freezing, freezing, right? So freezing क्या होती है हमारे पास? So you have a liquid, right? So you basically go from liquid to solid, right? Just imagine you're in your June, July. You basically fill out your ice bucket, ठीक है, or your ice container. You just put it in your freezer and it basically produces ice cubes, right? So what is freezing? When the state changes from liquid to solid, ठीक है? So it is called freezing, right? It is called freezing, right? Then again we have this freezing point over here, right? Freezing point, right? What is freezing point? Again, we have seen that in your melting point, right? It's similar, right? It is the point at which the liquid starts to convert to solid, right? Starts to convert to solid, right? Okay. So next change in state which we have in your bucket list is evaporation or boiling, right? Evaporation slash boiling. Evaporation slash boiling. Okay, so we have another important point in this. Here, you can ask the question, sir, what is evaporation boiling? Since both of them convert basically liquid to gas, right? So what is the difference between these two, right? The differences basically is important. But that comes into your exam. They ask the differences between evaporation and boiling, right? So we will do that in a while. So don't worry about that. So what is evaporation of slash boiling? So when the state, it is basically the change in state. It is the change in state. It is the change in state. It is the change in state from liquid to gas, right? Just imagine you're making a tea, a cup of chai at your home, and you basically do what? You basically boil the water first, right? Okay. So the water is boiling. You can see the water liquid is containing, it's basically producing steams. So liquid is converting into gas, right? That is boiling. Okay. Liquid to gas, right? And again, there is a question over here. Let me just keep it to first of all boiling, right? I'll explain evaporation boiling में difference क्या होता है. Okay, this is boiling. This is boiling. Okay, and let me rub these extra points. Okay. Again, there can be a question to you in your paper too. What is boiling point? Right? What is a boiling point? So boiling point again is the point. Let me just do that in the next slide because there is no enough space. Huh. So what is the boiling point? What is the boiling point? It is the point at which the liquid starts to convert, liquid starts to convert to gas, right? This is the called the boiling point, right? Actually, so now the important question which arises over here is that what is basically this, right? Let me write the question in a different color. Let me just choose a rainbow, right? The question is, okay, you can ask the question, sir, what is the difference? The difference between boiling and evaporation, right? It's an important question, which I also asked from my professor, right? So it can be of 6 marks, right? It contain basically 3 points, right? So let me just find a good video which would help you to explain. Okay, let me just give me just a second. Give me a second, right? Just give me a second. I have the video already with me. Let me just share the link. Okay, G, I have got the link.
Difference. Definition. Boiling. A process in which a substance changes its state from the liquid state to the gaseous state. Definition. In evaporation, a process in which a substance changes its state from the liquid state to the gaseous state without boiling. Process in boiling, rapid. Process in evaporation, slow. Temperature in boiling. Boiling occurs at a particular temperature. Temperature evaporation takes place at all temperatures. Bubbles. In boiling, it forms bubbles. Bubbles. In evaporation, it does not form bubbles. Energy. Boiling can occur using the internal energy of the system. Energy in evaporation, boiling requires an external source of heat.
This is just definitely.
So what is the difference between boiling and evaporation? What we're interested in is which particles of the liquid are involved and where. And at what temperature does evaporation and boiling occur? So, evaporation. On a cool day, a puddle will eventually evaporate, and that liquid will turn into a gas, into water vapor. It happens very slowly. Whereas if we're boiling water in a kettle, and we're putting in thermal energy from electrical energy, then it seems that this process happens much quicker as we create steam, which is water vapor, and that could actually boil that water into gas in a matter of several minutes. So what's happening from a particle perspective? Let's take a look. In evaporation, at any temperature, there is a range of energies that the particles have in the liquid. Some particles might be moving very slowly, in fact, probably a lot of them will be, and some particles, only a few, like these red ones here, will be moving very quickly. They will have enough energy, perhaps, to break their liquid bonds and escape as a gas. But they can only escape if they're near the surface. The particles which are underneath the surface, if they were to break their liquid bonds and become a gas, they would quickly collide with another particle and transfer their kinetic energy and form a liquid bond again. So they don't make it. So only the particles at the surface can evaporate, break their liquid bonds and become a gas. In doing that, they carry away some kinetic energy with them, and that reduces the kinetic energy of the rest of the particles, and so the average thermal energy of the particles decreases and everything cools down. That's why evaporation cools you down. What about boiling? Well, in boiling, we're constantly adding thermal energy from in the case of a kettle, from electrical energy into thermal energy. And this brings all of these particles up to a high state of kinetic energy. They are zipping around each other at maximum speed. In fact, they're going so fast now that any further energy that we put in will not make them go any faster in the liquid phase. What it will do is break the liquid bonds which are between the particles at the moment. And so that means that all these red particles here have got so much kinetic energy that any further energy we put in will break their liquid bonds and they become a gas. And that happens very quickly as we pump energy in from the kettle. It makes whole clumps of them become a gas, and that forms a bubble, which is why you see all these bubbles of gas forming. And that happens very quickly. The more energy we put in, the faster that happens. It's happening to the particles throughout the liquid, whereas evaporation, it was just the surface. In boiling, it's the liquid throughout. Okay, so let's summarize that in this table. Evaporation. Which particles are involved? And it's only particles with enough kinetic energy to break their liquid bonds at the surface, because only they can escape without colliding into other liquid particles. Evaporation. What temperature does it occur? It occurs at all temperatures. All temperatures for which the liquid remains a liquid and doesn't freeze or boil, so all the liquid temperatures. And we can say that that has a cooling effect. A cooling effect as particles escape, carrying away kinetic energy. What about boiling? Well, boiling, which particles are involved? Well, it's pretty much all the particles. They're all at the state where any further energy that is put in will make them break their liquid bonds. So all particles throughout the liquid. Okay, so this is a bulk property. It's happening throughout the liquid as we put further thermal energy in. At what temperature does boiling occur? Well, it has to occur once the particles have a maximum kinetic energy, and any more energy they absorb will break their liquid bonds rather than making them move faster. So it only occurs at the boiling point of the liquid. At the liquid's boiling point. There is no cooling effect. We're continuing to add thermal energy in the case of a kettle, boiling water, and so although particles are escaping with kinetic energy as a gas and carrying away kinetic energy.
Okay, so I hope that you got the difference, right? So it was a detailed video which I basically wanted you guys to watch in order to get an idea, because this is a very important question for you guys, right? And I have put it basically the places, the link over here for your reference, right? So if you want to rewatch it again, you can watch it again. Okay. Okay. So again, differences can you think about this? I have to again revise the differences. So the question should be now, what are the differences, right? Not is, there are many. What are the differences, right? So let me just make a table over here. So we have evaporation here, and then we have boiling here, right? We have boiling here. Okay. What is the first one? K, it basically occurs only at the surface. Only at the surface. Okay. The first one for this is it basically occurs throughout the liquid. Throughout the liquid. Throughout the liquid. And what is the second difference? That it starts before the boiling point, right? If I talk about water, so the boiling point for water is basically 100 Celsius, 100 degrees Celsius at sea level, right? So boiling will start after 100 degrees Celsius, and at and after 100 degrees Celsius, the evaporation can basically take place at any temperature, right? So it starts before the boiling point. The boiling point of any liquid, right? So for water, it is 100 Celsius. For mercury, it can be different, right? And it basically starts after the boiling point. Starts after after the boiling point, right? After the boiling point, right? The third one is it has no bubbles. Okay, it has bubbles, right? And I guess these three are enough for you guys. Okay. If you want to note down more, you can just use the video and basically note down the extra ones. Okay. Okay, G. So I hope it makes sense. So we have studied. Let's see what was written in your slide over here. So again, they are saying okay, solidification is what? When it is cooled sufficiently, the solidification occurs and it returns to solid state. See, that is called freezing, right? We have studied this in the next slide, which we have covered this change of state, that is called freezing. The density of material in its solid state is usually higher than its liquid state. So obviously, right, what is density? Density is mass upon volume, right? So if you basically go from liquid to solid, the volume has decreased, right? So if your volume has decreased, the density increases, right? The mass is constant, right? What is mass? The amount of particle, right? So number of atoms in the liquid or in the solid are same, right? So it is constant. Only the volume and the density is changing it. Okay. So now it is saying that when you heat the liquid, it basically causes the high energy particle to escape. Okay, and it's called evaporation over here, right? So when you have enough energy that you basically cross the boiling point, then boiling occurs, and the liquid turns into a gas, right? Okay, so this is basically the differences uh between just one difference over here between evaporation and boiling. We discussed these differences in detail in our slide, right? Okay, finally we have now gases, right? So what are gases? Again, let me just draw a 2D diagram over here of a gas structure. These are gases, right? So it will have this particle, and this particle, right? So again, let's talk about their properties. Let's talk about their properties. So again, they have no fixed shape. Okay, as you can see, let's think about any gas example. Let's say helium gas. Okay, obviously it has no fixed shape. It has no fixed volume, right? It has no fixed volume, but it can compress the gas, right? So that's the gas can compress into a cylinder also. Okay. You might have basically seen that in northern areas of Pakistan, when you go to, let's say, Iran, Pagan, you have cylinders of gases which are used for cooking, right? So it can be compressible. This is compressible, right? So this is the highlighting prominent properties of gas, right? They have no fixed shape, no fixed volume, okay, because they depends upon the dimension of the container, right? They can change, they can take the shape of any container, okay, depending upon the basically it can also be compressed, so the volume can also be changed, right? That is why it is compressible. Okay, so again, the gases, particle and gases are further apart, which you can see from this diagram, right? So the particles have no order, right? And they're able to move a bit, freely in any directions in the container, right? Randomly. So again, they're compressible, then liquids or gases, and they can expand again when they are heated, right? Then we have another state which is called basically condensation, the change of state. So let's discuss what is condensation, right? What is condensation? This is our change of state number D, right? That is condensation. So we have the D that is called condensation, right? So condensation is basically what? Just imagine you're standing in your, let's say you're washing your face in winters in from hot water, and when you basically open the hot water, you can see that the glass, right? Let's say if you're standing in your, okay, when you're washing your face, and you have, let's say, a wash bath, and you have a mirror over here, right? A mirror over here, right? And you are basically washing your face from hot water, and you can see the steam, right? The steam is glaring up, right? The steam basically builds up over here, right? So the gas basically when you are washing your face from hot water in cold winters, let's say the temperature is 15 degrees Celsius, and the water is basically at 31 degrees Celsius, right? So what happens? The hot steam basically, as soon as it goes into the environment, basically sticks onto your mirror as droplets, right? As droplets. Water starts to drop into from your mirror, right? That is called condensation, right? So condensation is what? It is the change of state. It is the change of state from from gas to liquid, right? From gas to liquid. So this is called your condensation, right? It goes from gas to liquid. Again, in this we have condensation point. Condensation point is what? Condensation point is again the point at which gas starts to convert to liquid, right? It is called decondensation point, right? I hope it is simple, right? So drops of water are formed when steam condenses on a cold window pane, for example, right? Again, we have seen this example. Okay, you might have been observing these right now because it is the winter season, right? The winter season, right? It's pretty simple, right? It's This is all which you observe. Again, physics is the study of physical world, which you can see, which you can understand, right? So yeah, now we have basically particles of particle model of matter, right? Okay, how are these states? Okay, what are these states and how are the particle arranged? We will study basically in the structure of solids and the property, right? Okay, so I'm going to just introduce you to the three states over here, and then we will basically go in detail about these three states in the next lecture, right? Okay. So again, what let's first of all read what is the book telling you guys, right? So again, let me just choose the highlighter yellow one and should do this. As well as being in continuous motion, the particles, atoms, molecules, ions, or electrons also exert electric forces, right? Obviously, they are in a fixed shape. So there might be some forces which is keeping the structure together, right? Either it is liquid, solid, or gas. So these forces can be both attractive or repulsive, right? So basically, the attractive force holds the particle together so that they cannot basically escape away from the structure, and the repulsive force basically resists compression, right? So if you try to basically compress the solid, it will basically the repulsive force will basically not allow the atoms to overlap because the nucleus are a positive charge, right? So if you know that positive will repel, right? So similarly, nucleuses are positive, so they will basically repel each other. That is why solid is basically incompressible, right? And the particle model can explain the existence of solid, liquid, and gaseous state, right? Again, the way the particles are arranged basically can define that how can I call a particular state to be solid, liquid, or a gas, right? The particle model, and that is called particle model of matter, right? So we have seen the states and the change of states. Before in this particular lecture, we have studied okay, what is matter and what are the states. Again, solids, right? So let me just take a snap from here. We'll discuss this over there. Okay. Here. Yeah, this is a solid, right? And let me see if it is recording. It's recording. Thank God. So first of all, I will ask you guys. We have done this already, right? So just tell us a quickly think about the structure of the solid, right? How is the structure by just seeing the diagram, right? You can just pause the video here and just think about the structure over here, right? Okay, I guess you might have thought about this, pondered over this. First thing which you might have observed is okay, it has regular regular structure, right? Or the better word to you basically describe this is it is uniformly arranged, right? It is uniformly arranged, right? It is uniformly arranged, right? The second thing which you might have observed that it has not enough spaces, right? Enough spaces, right? The third thing which is the property ठीक है, which you will understand if you are observing it under a microscope, that the particles are in constant motion, right? They are in constant motion. Because constant motion exists, right? So let's see what is the book stating over here. So in solids, the particles are close together, right? You can see that from this particular diagram also, right? They're pretty close to each other. And the attractive and repulsive forces between neighboring molecules balance, right? Why are they balancing out? Because they are yeah, they are uniformly arranged, right? So they are not getting repulsed or they're not getting basically scorched from one side, right? They are uniformly arranged with uniform spaces, right? You can see the spaces between the particles layers are pretty uniform, right? Right? You can see these spaces, right? Because that means okay, the forces are balanced out, right? Again, each particle vibrate about fixed position. So by particles are vibrating by remaining in their fixed position, right? So again, they are arranged in a regular repeating pattern like those formed by crystalline substances, right? So crystalline substances हमारे पास कौन से होते हैं? You might have studied this in chemistry. I don't want to go in this detail, right? So it's sodium chloride, right? It's salt, right? This salt is basically a crystalline substance, right? So it has repeating units of cubes. Okay, so they have, and if you zoom in into the salt particle, you would observe a cube structure which is repeating, right? So it has a crystalline substance, right? Okay. Chari. Then we have properties over here. Figure 2.1.3, right? Okay, so what is it saying? So what is figure 2.1.3 was basically NaCl. So this was the structure over here. This was okay, Na. This was Cl. This was Cl. This was Cl. Right. So these are forces of attraction like these. Right. And then we have Na. Right. We have then Cl, Cl, then Cl here. Right. It's sort of a cuboid structure, right? So this is in what was shown in figure 2.1.3. So there were some forces, right? Sodium is positively charged, chlorine is negatively charged, right? So again, you can see that ठीक है सो यहाँ पे हमारे पास होगा Na यहाँ पे इस साइड पे Na होगा हमारे पास which is basically attracted over here we have Na here positive so there is a force of attraction here right so if you basically have a positive charge and a negative charge you might have seen that you might also know if opposite charges attract so they will attract each other right so what is happening uh basically electric forces exist basically between the particles which is basically causing them to be together right which holds them together and determine the forces and distance between them right so you can see this particle over here okay, they have some spacing and they have some regular pattern over here right and this is also keeping the structure together so the spacing is caused by repulsive forces, and the layers, the solid structure, basically, which is keeping the particles together, not letting them go away, is basically attractive force, right? So these are called electric forces, right? Because ions, okay? So you might have heard the term ions, right? So ions are what? Basically, they are charged atoms, right? What are charged atoms? Okay, you can see over here that sodium has a charge of positive, right? And chlorine has a charge of -1. Okay, so you can see that it has a charge. These are called ions. So these basically causes the electric force to exist, right? And these basically keeps them together, right? These forces enables the solid to keep a definite shape and volume. Okay, that is the point. That how is the property of fixed shape and volume arriving because of this electric forces that is basically uniform, right? While still allowing the individual particles to vibrate backward and forward. Right? So you can see in this particular shape, every atom is basically vibrating by remaining in the fixed shape, right? But they are not getting away, right? They are not getting away out of the entire structure, right? Owing to the strong forces between particles, solid resist compression, expand very little when heated, right? Again, they're just saying it is the property which we have studied in solids, they were incompressible. Okay. Why they were incompressible? Because they had not have enough spaces, okay? And because of strong forces, the atoms are pretty close to each other. They had not have enough spaces. If you try to heat up with a lower temperature, okay, they will not expand so much. If you provide a very huge amount of energy, it might convert to liquid, right? That is called melting, right? So just defining the properties which we have seen and studied in the last lecture, right? So just a detailed overview which we have studied also already, right? Okay. Then we have liquids, right? So liquids की हम ले लेते हैं snap, listen to study and guess and predict what will come in the upcoming lecture, right? Upcoming sites. So again, we have solids here and then we have liquids here, right? So I'm going to ask a question again to you guys. Again, by just seeing a diagram over here, by just seeing the structure over here, I want you guys to guess. I want you guys to guess. Again, we have already studied the property, right? Yeah. Just recall, not guess, just recall what are the properties of the right? So you can just pause the video here. Oh, I hope that now you have thought about this. So let's now quickly recall. Okay, so from just seeing this particular structure, you might have recalled that it has no fixed shape, right? You can see that particles are not arranged uniformly. It has no fixed shape, right? You can see it has greater spacing, greater spacing, as compared to solids, right? As compared to solids. And the last thing which should be in your head, which is that it has fixed volume, right? Because the particles are not escaping, right? The particles are again inside this entire volume. Okay. To try to count the number of particles here, it will come out to be same, right? From this. It just have enough space, right? It has fixed volume. Okay. So yeah, I believe that you all got it right, right? And let's now go through what is the book trying to convey to us, right? Let me just save it first in case of if it crashes. Okay, structure. ठीक है? So again, they are just stating what we have just already discussed. Liquids, the particles are slightly further apart than in solids, right? But still close enough to have a definite volume, right? We have seen this. So you just see this diagram and you can just obviously feel it out, right? Again, the of every particle in the entire universe in any state is basically constantly vibrating, right? So they can at the same time move rapidly over short distances, slipping past each other, right? Since they have spaces, they can move in this direction. I also feel like they can move past each other. Okay, let's say this particle can move in this direction, this particle can move in this direction, okay, so on and so forth. Right? So they are free to move within the volume. Right? Within the volume. What is the point? Okay, they are free to move. They are free to move within the volume. Right? Within the volume. Right? I hope that makes sense to you guys. Right? Okay, so this the structure, right? So the detailed again discussion was in the first lecture. If you do not recall it, just go and watch it again, right? Okay. प्रॉपर्टीज ठीक है जी अब प्रॉपर्टीज जरा डिटेल में बात करते हैं स्ट्रक्चर का हमने देख लिया कैसा होता है पार्टिकल कैसे मूव करते हैं प्रॉपर्टीज कैसे देख लेते हैं राइट अगेन वी हैव स्टडीड दिस ऑलरेडी सो इट्स जस्ट एन ओवरऑल डिटेल्ड वर्जन ऑफ how is the property of liquid exist the way we have discussed, right? Why is it? Okay. So in a liquid, forces between particles are less than in solids, right? If the forces are less, that is why they have enough spaces, right? Because that is why they are further apart, right? Because these strong forces hai hi nahi, which can basically keep them together, right? In a uniform shape as in liquid, as in solid, right? So you can just now write this point over here that forces in liquid between particles is less than forces between particles in solids, right? This is very important point over here, right? That is why they have spaces, right? अच्छा जी. Liquids have definite volume, but individual particle can slide over each other and are never near another particle long enough to get trapped in a regular pattern, right? This is just a pattern stating कि why do they have fixed volume that they have a fixed number of particles. The particle cannot escape the boundary of the liquid, right? They are inside the liquid, but they have enough spaces such that each particle can move to and fro between each other, right? But they cannot be hold together in a fixed shape like this. Okay? The particle will not, they will never basically attain the shape like this until you basically undergo freezing, right? Okay. This is again liquids to flow, right? Again fluids, right? What are fluids, by the way? Fluids basically contained liquids and gases, right? Combined, the we call liquids and gases combined together to be fluids, right? And what is the special property of these things? That they can flow, right? They can flow. Flow means कि if I just pour the liquid on the floor, they will flow in any direction, right? Similarly, if I basically do a room spray in my room, the particle will spread out randomly in any direction, right? They can flow, right? So again, they can take the shape of the vessel containing them. Okay, so again, it has no fixed shape. It can contain the shape of any container in which they are put in, right? The forces between particles strong enough that liquids only slightly more easily compressed than solids, right? Again, they just we have studied this already. They are compressible, slightly greater than solid, right? But not completely easily compressible, right? So yeah, this is a debatable point. I want you guys to research on this, right? So this is a question over here. So research on this. I will basically ask for you guys to update on me on this particular point after one day, right? As soon as I upload the recordings, right? So yeah, research on this. research on this. Okay. So when heated, the particles move further apart, enabling liquids to expand more easily than solid, right? Again, because they have enough spaces, right? Need to provide less energy than solids because they have less attractive forces. The forces in liquids are weaker as compared to solids, so we need to provide less energy for them to expand, right? I hope it makes sense, right? So again, as the temperature increases, the particles vibrate more, okay? As they vibrate more, they have enough kinetic energy, okay? And which can result in evaporation of liquid, right? Let me explain this. Let me explain this hota kya hai, okay? Enough. Let's say if I provide it with heat energy, right? What happens? Let's say if I'm heating it up, right? If I'm heating it up, I'm heating it up with a candle, right? Let's say. So what happens? The particle will start to vibrate, right? Will start to vibrate more rigorously, right? They will start to vibrate more rigorously. Okay. So the speed of the particle would increase, right? And we have seen the formula for kinetic energy. What is the formula for kinetic energy? It was basically half mv square, right? It's pretty simple. To try to relate kinetic energy and speed, it is directly proportional to speed square, right? So if your speed is increasing, the kinetic energy will also increase, right? So that is the relation, right? So if your particles start to vibrate more rigorously, you will have more kinetic energy, right? I hope it makes sense now, right? Okay, this is a very important point over here, right? So this is the energy which basically causes the particles to vibrate and again lead to a change of state also, right? Right? And then evaporation हम बात कर चुके हैं. What is evaporation? That it basically converts the liquid into gas, right? At any temperature. Okay, जी? Just it should have enough energy just to break the bond, right? Okay. Gases, right? Gases. So let's go and discuss what are gases. Let me just snap the diagram of the gas particle. You can see first of all over here that the number of particles has reduced in gas, right? So we can it has basically less number of particles available in this particular area. So that means that some particles have escaped, right? That leads to a fact that it has no fixed volume, right? I hope it makes sense. You can just go back and rewind this part again and watch it again, right? This is very important. So let's study this, right? Let's study this. Okay. So again, I'm gonna ask the same question to you guys here. Just by just seeing the by just seeing this diagram over here that is 2.1.2c. Now I want you to recall the properties of gas. You just pause the video here and just rewind it and just recall it, right? Okay, Ji. So I hope that you might have thought about it and you might have got might have recalled the properties again from just seeing it. You can just see it has no fixed shape because the particles are arranged randomly, right? It has no fixed shape. And as I told you guys before, that number of particles are reduced, so it has also no fixed volume, right? It has no fixed volume. And the last thing again, since it has huge spaces, I can basically decrease the spaces by compressing them together. Okay, okay, and I can just bring them together closer apart to each other. Okay, so it is pretty easy to compress. Okay, so it is compressible. It is compressible. Okay, to a great extent, right? So I hope it makes sense over here. Okay. So now again, let's talk about the structure, right? Structure होता क्या है हमारे पास structure के बारे में बात करते हैं. So what is the structure and how it looks like? So structure basically in the structure we are talking about कि how the particle arranged and how are they moving, ठीक है? And what basically can lead to basically a change of state in this particular state of matter, right? Okay. So in the particle gases are much further apart than in solids and liquids over here. About 10 times, right? You can see the spacing between the solids and the gases over here. But it has increased about 10 times. Okay, that is pretty easily observable over here from so compare picture A and C, right? At the bottom side. Okay. So now and so gases are much less dense, okay, and can be easily squashed. Okay, they can be squashed to smaller places that is state is compressible. Again, what is density? Density is mass upon volume, right? So if your volume is huge, that means your density has reduced, right? That is why gases are less dense, right? Again, particles dash around at very high speed since they have enough spaces. They are basically can move around freely, and that means particles can move around at very high speeds also, right? About 500 meter per second for air particles, right? At 0 degrees Celsius, right? So it is only brief during brief spells when they collide with each other and when the particles collide with the surface of the container, right? Again, they are saying that it has enough spaces to basically, let's say this is particle one, this is particle number two, this is particle one, this is particle two. It's pretty rare for particle one and two to collide with each other, right? Because they have enough spaces, they can move randomly in any direction. So the chances for colliding with one and two are pretty rare, right? And with the walls of the containers, because they have enough spaces, they will take a huge amount of time to basically collide, right? Okay, it's random, right? It's particular, it's very random. Okay, now let me just save it and to the properties over here. Owing to the high speeds, obviously we have seen the relation that kinetic energy is proportional to velocity square, right? If they have very high speeds, they will have high kinetic energy, right? So the large distance between the particle and gas and the interaction between them is small, right? So again, they're saying case they have very weak forces, which is basically keeping them together. So the forces of attraction between gases is less than the force of attraction between liquids, and the force of attraction in liquids is very less than the force of attraction in solids, right? So that is how you basically relate these three forces of attraction together, right? It's pretty straightforward over here. Okay. Okay. So let's move on. Okay. So again, so due to this, okay, they are pretty further apart. So they have no fixed shape. So okay, and they have no fixed volume. The volume is basically determined by the volume of the container. It can change depending upon the volume of the container. So it has no fixed volume. And they are easy compressible and they can expand much more than solid liquids because they have very weak force of attraction between each other. So it is pretty easy to provide. We can just expand the gas by providing in very less amount of energy as compared to solids or liquids, right? Because the force of attraction is very weak in gases, right? Okay, so this basically ends the states of matter all apart. Okay, that I told you in the start that we talk about the first thing over here, which is A, this, and then we have relations over here, right? Okay, what are the relations of pressure and temperature and volume, pressure and volume, okay? And what is the combined formula which will basically relate these things, right? In which you basically are tested on numericals, right? Okay. So now we have relations of temperature and kinetic energy, right? It is a pretty interesting relation, right? First of all, I would want you guys to think about this, right? How can I relate temperature and kinetic energy? Okay. How can I relate temperature? How can I relate temperature and kinetic energy? Right. So for this, I would want you guys to pause the video and think about this, right? Pause the video, think about this, and let me know. Let let me know your comment. You just comment basically in the WhatsApp group while watching the recording, right? You just tagging me, sir, I'm watching this, the lecture number two, and I think at this point that, and that will be a point of view. Hello guys, welcome. I hope that you thought about this and what is the relation of temperature and kinetic energy. So for that, let's go to a blank slide and let's see what happens, right? So let's go to a blank slide and let me draw a shape, right? Let me just draw a container, a 2D shape, okay, for this reference. Okay, this is basically when you increase the temperature, right? Increasing temperature, right? Increasing temperature. Okay, and let me just draw the particles over here. Let's say these are the particles, right? Let me just draw them. Let's say it's a liquid, right? Okay. And what is happening right now over here is I'm heating it, right? I'm heating it. So I'm increasing the temperature of the container, right? So what happens as I increase the temperature? The particle starts to vibrate, right? They starts to vibrate more. Okay? They start to vibrate rigorously. Let me just draw the vibrations, animations, right? They start to vibrate rigorously, right? What happens as I heat it? So they start to vibrate rigorously, right? Rigorously. They start to vibrate rigorously. Okay. And it's recording, like confirmed. Yes, it's recording. That's what. Okay. And as soon as they start to vibrate rigorously, okay, they basically attain high speeds. They attain high speeds, right? And since we can relate kinetic energy and speed by the following relation, the kinetic energy is proportional to speed squared. So as soon as the speed increases, so does the kinetic energy, right? So increasing temperature has this effect. So if you increase temperature, if you increase temperature, so kinetic energy of the particles also increase, right? So it's a direct relation with the kinetic energy. Let's see what happens if we basically decrease the temperature, right? So decreasing the temperature, decreasing temperature, right? Let me just copy, let me just make it again. Again, you have a container 2D shape over here, and let me draw the particles with green color. Okay. So what happens as I decrease it? Okay, so basically, when I decrease the temperature, the particles basically start to move slowly, right? Their motion basically decreases. The relative speed of motion decreases, right? So the arrow gets smaller, right? You can see that. Okay. So what happens? They basically, as soon as they decrease the temperature, so I'm cooling it, right? Let's say I'm cooling it, right? So what happens as I cool it? So they basically start to vibrate slowly, right? They start to vibrate slowly, and as soon as they start to vibrate slowly, okay, they attain basically slower speeds, right? They attain slower speeds over here. And again, from the relation which we have got from kinetic energy formula, the kinetic energy is directly proportional to speed squared. So what is happening over here? What is happening over here? As I basically has obtained slower speeds, so kinetic energy of the particle will also decrease, right? So again, if I basically decrease the temperature, if I decrease the temperature, so does the kinetic energy, right? So decreasing temperature decreases kinetic energy, right? So it's again a direct relation over here. So this is the relation of the temperature and the kinetic energy, the average kinetic energy of the particles overall, right? I hope it makes sense. So this is exactly written over here in your slides. Let me just recap it. Let me just read for you guys. So I'm sorry that room temperature, the particles vibrate about fixed positions, right? They have no enough spaces to basically move freely. When energy is supplied to the solids and its temperature increases, the particle vibrate more strongly and average kinetic energy of the particle increases. Okay. Again, we have obtained that temperature is directly proportional to kinetic energy, right? So increasing temperature increases the kinetic energy, right? So when the temperature is reduced, the average kinetic energy of the particles reduces, and eventually the temperature is reached where the particles ceases and the kinetic energy is zero, right? So as soon as you, let's say, keep on dropping the temperature, and as soon as you reach negative 273 degrees Celsius, that is the absolute zero temperature. Okay, so what is the importance of this? This is the lowest temperature possible, right? This is the lowest temperature possible. It is the lowest temperature possible, and at this particular temperature the motion of the particles are approximately zero, right? So this basically is uh this is the lowest temperature which have been possible, and in this vacuum in a space where we have basically no air particles, the temperature is basically the lowest side. That is why if you, let's say, accidentally go out of the satellite without the spacesuit, we freeze to death instantly, right? Okay, so pressure and kinetic energy, right? So again, what is pressure first of all? Let's talk about pressure, right? So let me just first of all summarize this entire content in a slide, right? Then we'll talk about this. Okay, so we're talking about pressure and kinetic energy. Pressure and kinetic energy. right? So before starting, first of all, let's assume that we have a cube over here, right? We have a cube over here. We have a cube over here, right? Let me just zoom talk about this one particle. See, so this particle basically, let's say this motion, this particle moves here with a certain force F, and it collides with this particular area that has the cross-section area A, right? So since from the formula we have this, that pressure equals to force upon it, right? So what happens over here, right? First of all, let's say this is a gas, right? Inside this container we have gas particles, right? So particles in gas are in continuous random motion, right? Continuous random motion, right? So let's say this is alpha. Particle alpha. So particle alpha collides 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 with the wall with force F and cross sectional area A, right? And cross sectional area A, right? So since from this relation the pressure is force upon area, so the particle alpha exerts a pressure on to the walls of the container, right? Walls of the container. Okay. So now let's imagine all the particles colliding, right? This particle colliding with this particle colliding with this wall, particle colliding with this wall, this particle colliding with this wall, right? So I can say the fourth point to be as the average pressure exerted, exerted. Let me just fix my spelling. Exerted by the particles, by the particles onto the walls of the container, of the container is called the pressure of the gas, right? Pressure of gas, right? Acha, अब how can I relate pressure and kinetic energy, right? So how can I increase pressure? So either by two things, right? We can say that pressure is directly proportional to force and pressure is inversely proportional to area, right? So we have two relations in this formula, right? So let me just make a box over here to just separate this. So what happens if I can increase the pressure by directly increasing force, right? And this will increase the pressure, or I can decrease the area and this will increase the pressure, right? Okay, I just want a greater number of collisions with the wall, right? So if I have greater number of collisions with the wall, that will have greater pressure, right? So for this, I can basically do what? Let's say, so we have the relation of pressure and kinetic energy, right? Let's say if I do what? If I increase the temperature, right? So if I increasing temperature, increasing temperature does what? Causes particles to move with greater speed, with greater speed, right? And from the formula which we have, the kinetic energy is directly proportional to speed square. If you increase the speed, so does your kinetic energy increases, right? So what happens? So if a particle is moving at greater speeds, so it will collide with greater forces, right? So it will have high kinetic energy, right? So if we have high kinetic energy, so what happens? So the collide, particles collide with greater forces, with greater forces with the wall, right? with the wall. So again, we have the relation that pressure is directly proportional to force. So if we have greater forces, we will have a greater pressure, right? So what is the relation of pressure and kinetic energy? That they are directly proportional to each other, right? So if we increase the kinetic energy of the particles, okay, by fixing the area to be constant, we will have higher pressure, right? So this is the relation with pressure and kinetic energy, right? I hope it makes sense, right? So it's just a small story, and if it makes sense to you guys, it will be pretty simple to understand for the future, right? So I hope it makes sense. Okay. So again, let's see what is this particular content from the book saying. So all the particles and gas are held in rapid random motion with a wide range of speeds and repeatedly hit and rebound from the surfaces of the container, right? In huge numbers per second. This causes a force at right angles to the surfaces of the container of pressure. When the temperature of the gas rises, so does the average speed and kinetic energy. Collisions with the surfaces of the container occurs more frequently. It basically increases the pressure, right? Again, the summary is that pressure is directly proportional to kinetic energy, right? So this is the relation of pressure and kinetic energy, right? Okay, I hope it makes sense, right? Unmute myself. Yeah, I hope it makes sense. And it's pretty simple, right? Straightforward. Actually, the next thing which we have discussed temperature and kinetic energy. We have discussed pressure and kinetic energy. Let's discuss pressure and this is just stating the last thing which we have studied. So let me just do this. Okay, I'm going to take it up here, right? Further, what are they saying? Force and gas pressure, right? So this is just the thing which we have discussed, right? Okay. So for at each collision of a gas, we have with the surface of container, we have change the momentum, right? So we will study this in topic 1.6. Okay, what is this, right? Don't worry. So we have seen this relation. We have already studied this, by the way. Because the force is equals to rate of change the momentum, right? Okay. So as soon as the ball collides, let's say this is the wall of the container, and this is the particle, right? So as soon as it combines, this has mass m. It goes with the speed v, right? So it comes back with a speed, let's say v also, right? So it has a change in momentum, right? That would be what? 2 mv, right? 2 mv. So this is basically the change in momentum. And for the collision, it basically collides with the wall for some time, delta t. So the rate of change in momentum is basically force, right? So at constant temperature, the average force and hence the pressure exerted on the temperature on the surface is constant, right? So if you have a constant temperature, so it will not cause the particles move at higher speeds. So if it is not moving at higher speeds, if it is moving with constant speed, so the pressure remains constant, right? So what is pressure? Again, we have seen that pressure is basically force per unit area, right? Pressure is force per unit area, which is written over here. So when the temperature rises, the average speed of the particle increases and changing momentum with the walls of the container also increases, and that increases the force. And if the force increases, so does the pressure, right? Again, which we have studied, this is just the thing which we have studied in the last slide. That is stated again that pressure is directly proportional to kinetic energy, right? And increase in kinetic energy basically leads to an increase in pressure P, right? So yeah, I hope it makes sense. Now we have the last thing to cover in today's lecture. That is pressure of a gas, right? So let's start with this. Before starting off this, uh, I want you guys to think, okay, let's say if you have a juice container, and if you take the juice container, empty juice container, plastic one in the vacuum, what would happen to the container? Think about this. Pause the video, think about this. Okay, so pressure of a gas. We have seen this already. Yeah, I guess I have talked about this in another group. So let's just see the bottom line diagram over here. The can, right? It is the plastic can over here. So initially it is at its default state. ठीक है atmosphere के अंदर रखा हुआ है. So it's not crumpling, right? So then I'm basically extracting all the air inside the can using a vacuum pump, right? Then what do you see over here? What is happening? You can see it's basically crumbles, right? It crumbles up. So can you think about this? How is extracting the air inside the can causes the shape of the can to be on the bottom, right? It crumples. Why does it crumple? Okay. So think about it. Then pause the video and think about the uh, about this particular step in which I made it. Okay. So yeah, acha, you can also do one interesting thing over here, which is this. You can do ink replay. Okay, so it will basically play the video from the start. Okay, so I can increase the speed. Okay, so if you want this to be, I guess recording and that will be clear. Okay, so yeah, okay. So what is happening over here is as follows. Let me first of all read the content and I'll explain क्या हो क्या रहा है. So air forming the Earth's atmosphere is called basically stretches again a long way. It is called the Earth's atmospheric air, right? So it contains nitrogen, oxygen, argon, and helium and other gases, right? So air has weight, right? So air in a normal room weighs about the same as you do, about 500 Newton, right? That's a huge, right? So air, obviously air has particles, right? Particles has masses and masses has weight, right? Because of gravitational field strength. And you know how to find weight. The weight is basically mass times gravitational field strength, right? The weight of the air is around 500 Newton. That's huge, right? Okay. And we have seen that one atmospheric pressure is what? It is basically 1 exponent 5 pascals, right? We have seen that in the last lecture, right? Pressure together. With 1.5 Pascal, which is also written over here. We can also write, then we can also know that Pascal, 1 Pascal is also equals to 1 Newton per 1 meter square, right? So this is also written over here. It is either Pascals or Newton per meter square, same. So atmospheric pressure acts equally in all directions, right? So let's say if you're standing right now and you have a normal phase, right? If you go to vacuum, your air inside your body will cause you to explode, right? Because the space has vacuum, it has no air. If there is no air, there is no atmospheric pressure. Okay, so that is why we have space suits, right? And also the temperature is absolute zero. You freeze to that plus explode, right? So let's see this diagram over here. This particular diagram one and this particular diagram two, right? So in one, what is happening? There is basically some air inside this can and there is air outside, right? So since both of the sides contain air, so it will exert an equal forces in inside the can and outside the can, right? So the outside pressure is trying to basically squeeze the can, right? But air is basically inside the can also, which is also pushing equally in opposite direction. So it keeps the can in this particular shape, right? As soon as you basically extract the air outside, inside the can, so there is only air outside, right? So it is exerting pressure from the outside, right? Since there is nothing to basically counteract, so the body of the can crumples, right? Okay, so this is just explaining that how does the pressure of a gas leads to you guys having constant shape or any other uh, non-living thing like a can having its normal shape, right? So in designing things, we basically consider these things, right? So effect of on pressure of a change in temperature, right? Constant volume. So let's start from here. We know now that what are some phenomena, that is what is pressure of a gas and how does pressure and kinetic energy relates, right? So we will be moving to go forward in this particular topics. Okay, and then how does kinetic energy and temperature relate? So kinetic energy is the main crux over here, right? So everything, temperature and pressure are getting related with the kinetic energy, right? So how do they relate? And these things will be carried forward in the next lecture. Okay, so let's start from here, right? So what is the effect of on pressure of a change in temperature, right? So we are keeping the volume fixed over here and we are basically varying two things over here, right? So we can only observe two things simultaneously. Okay, let's say pressure and temperature, pressure and volume while keeping temperature constant, right? Let's say if we have pressure, effect of pressure when temperature and volume both are changing, that would become complex to basically observe, right? So we can only observe two temperature quantities because we always observe, we do some experiments and we basically plot some things on the graph. Let's say the temperature is here, the pressure is here. We basically try to correlate them, right? So what is the relation of pressure and temperature? Is it direct proportion? Is it inverse proportion? So on and so forth, right? So let's focus on this point, right? It has constant volume, right? It has constant volume. Just imagine this container. Let me just rub this first. Just imagine this container over here. Let's say we have two containers, container A Let me just make it over here. Is it recording? Yes, it's recording. Okay, so we have container A over here, and then we have container B over here, right? So let's start two scenarios. Let's say this is container A, and then this is container B. It has, let's say, particles. It has liquids here. Let me just make the liquid color, liquid surface here. Looking good. That's good. Okay. Okay. Okay, Ji. So let's see what will happen. Let's say this is at room temperature, right? And the pressure is constant, right? The pressure is atmospheric pressure, right? The pressure that is exerted by the atmosphere, right? That is air. So air is surrounding this particular container. And similarly, air surrounding this particular container over here. The pressure is constant, right? So the pressure at the liquid surface is constant. That is pressure of atmospheric pressure. And from the last lecture, we know this value is 1 x 5 Pascal, right? 1 x 5 Pascals. So our pressure is constant. We're not compressing, or we're not basically, let's say, changing the pressure on the particle of the liquid. It is just we are heating it up, and we're just checking what is the, sorry, basically over here we have constant volume, right? So yeah, let me just fix it out. We have constant volume here. Okay, so now this would be different. I basically correlated the other scenario, which is in the next slide. So let me just fix it. Okay, now let's see, we have container A, which again has now gas, right? Because we want to compress it, we want to change the pressure. Okay, so we have container A, we have container B, and we have some pistons, right? We have some pistons over here, right? This is gas A. Let me just label it here. This is gas A, this is gas B, and we have another piston here, right? Let me just compress it further. Okay, so what would happen if we do this? So we have the particles. Let me draw the particles of gas A. They are further apart, right? And let me draw the gas particles of gas. We have the same gas, right? But we just basically compressed it, right? So we have 1, 2, 3, 4, 5, 8 particles here and 8 particles here, right? Okay. So we're basically applying a force here, right? We're increasing the pressure. This is pressure 2 and this is pressure 1, right? So what is the scenario over here? Pressure 2 is greater than pressure 1, right? So obviously we have studied in kinetic particle model of matter, right? In the last lecture, that particles are continuous motion, right? First of all, let's read the content. What is the content saying, right? So when a gas is heated, its temperature rises, the average speed of the particles increases, right? If the volume of a fixed mass of a gas stays constant, its pressure increases because the changing momentum per second when the particles collide with the surfaces increases, leading to a larger force per unit area and hence pressure, right? Okay. So either way is fine over here, right? So we have constant volume here. That is the amount of particle that it is colliding, right? So let's use this same example over here. Basically match with the content of the book, right? So now they're seeing basically over here is the following thing, right? So now they're seeing the following things over here. That is, so you have two containers. So let's match the example of the book just to stay consistent. So now simply what is happening over here, you have container A, you have container B. So we're just heating it up, right? Let me just match the dimensions, right? And we have the same liquid volume, right? Let me just fix the volume, right? It's the same volume here. It's the same volume here, right? So this is the V is constant. The volume is constant. The volume is constant. Okay, so basically now you have container two. We have two containers which has constant volume. That is the amount of liquid in the container is same, right? Okay. So now what is happening? So we are basically, let's say we have these particles in liquid A. right? Or let's say gas, let's keep it gas. Either way is fine, right? So I'm gonna keep it liquid air, right? Let's say this is liquid air, and this is liquid B, right? So now we have basically increased the temperature. We are heating it up, right? So let me just draw a candle, beautiful candle. It should be like this. Okay. So basically heating it up, right? We are heating it up. So again, this is liquid A for just labeling it. So what would happen now, right? So the particle will start to vibrate rigorously, right? As we have seen in the last lecture. Okay. So the volume is constant. So what is happening over here? Let's dictate the step-by-step procedure. So let's say we have heating up, heating up the liquid, heating up the liquid does what? It basically causes the particles to vibrate rigorously. Rigorously means faster, right? And since they are basically vibrating fastly, so they are moving at high speeds. So they have attained high speeds, right? They have attained high speeds. And since we know the relation of kinetic energy and speed, that is kinetic energy is directly proportional to speed square. So if I basically have increased the speed, so thus my kinetic energy have increased, right? So again, first of all, then what is pressure? Okay, so since they are moving at very fast rates, so the collisions, the basically the particles are colliding with each other and with the walls of the container at very fast rate, right? So since we know that force is the rate of change of momentum, right? And what is rate of change of momentum? That is mv minus u divided by t, right? So since the speeds are increased, okay, so does the numerator has increased, right? The numerator has increased since change in momentum is proportional to force, so does your force increase, right? So the force applied by the particles during the collisions with each other and with the walls of the container increases. And since we know that what is pressure? Pressure is force upon area, right? So if your force has increased, so does your pressure increase, right? So therefore, we can basically say that pressure is directly proportional to temperature, right? So if basically I increase the temperature, so will basically my pressure will be, right? So pressure, if your temperature increases, so does your pressure, right? So let me just draw the relation over here so it will make sense more. So let's say this is temperature over here, let's say this is in Kelvin, and this is your pressure which is in pascals, right? If I want to draw this relation, that would be as follows, right? So let me just draw the relation over here. It's going to be direct proportion, right? So if your temperature increases, so does your pressure increase, right? So they are directly proportional to each other, right? So let me just, this is the graph over here and this is the relation, right? That pressure is proportional to temperature, right? So this is your entire relation. Let's say if you have constant volume, if you're varying pressure and temperature, so this is how they will basically interrelate. Okay, now we have effect of volume and temperature, right? So we are relating basically volume and temperature, right? So while keeping what? While pressure is constant, right? So the pressure is constant, right? Okay. So now let's see what are they saying. What is the content of the book saying over here? The particles in a gas are free to move and they are moving rapidly and they fill the entire volume of the container, right? So the property of a gas that they can take the shape of any container since they have no fixed shape, right? And they are free to move, right? So they have move at very high speed since they have very weak force of attraction between each other, right? So when a gas is heated, the temperature rises, right? And the average speed of its particle increases as we had done in the last wall part. That if you increase the temperature, the particles start to vibrate more. That means that they have more collisions with the wall and with each other, right? That means that they're providing a greater force, right? So if the pressure of the container remains needs to remain constant, so the volume of the container must increase so that the frequency of the collision decreases. This means expansion of the gas must occur, right? So what is it saying? Right? So let me just try to relate this with an example, right? So let me just dictate the algorithm. What is the algorithm which they are saying over here, right? So again, what we are trying to do, we're trying to basically find out the effect of basically volume and temperature, right? Volume and temperature, right? And while keeping what fixed, what is fixed over here? Let me just write it down over here. The pressure is constant, right? Pressure is constant. Hey, this is very important over here. Pressure is constant. Okay. So what is happening, right? So again, we have a gas. Note, don't forget to no basically forget the formula over here. So we'll use these two formulas over here. That force is change of momentum, rate of change of momentum, right? And the pressure is force per unit area, right? Okay. Okay. Let's start. So basically, we're heating up the gas, right? So heating up the gas, heating up the gas does what? Causes the particle to move faster, right? Causes the particles to move. Acha, you will find this law in the future slides that this is also called some sort of law, right? We have Boyle's, Charles, so we identified. You can pause the video here and just make a guess over here. Is it Charles law? Is it Boyle's law, right? What is it? Okay, so causes the particles to basically move faster, right? So since they are moving pretty fast, so they collide with the walls and each other at a greater rate, right? That means that they are having greater collisions and they are basically colliding with a greater force, greater rate and force, right? The force with which they're colliding and the number of collisions with each other and with the walls have increased. Okay, that basically dictates what? That your force has increased, right? So they're colliding with the wall with a greater force. And if you relate this formula, that force is directly proportional to pressure, right? The pressure is directly proportional to force, right? So what happens? Actually, what should happen? The pressure should increase, right? Pressure should increase, right? Pressure should increase. But what is the condition over here, right? Okay, this is the actual fact over here. But we want to basically make sure that pressure is constant, right? That pressure remains constant. Okay. So for this, what can we do? Right. So what is basically pressure dependent upon? Okay, let's try to relate this. Pressure is proportional to force, and force is proportional to what? The rate of change of momentum, right? So what basically when we heated up the gas, what happened? The speed with which they're colliding increases. So rate of change of momentum basically increase, right? So changing momentum increased. So this basically increased what? Increased the force that with which the particles were colliding with each other and with the container. So this basically increased the pressure, right? So we want to basically now uh alter in such a way that the pressure remains constant, right? It should remain constant, right? So let's see what is happening over here, right? Let's say we have container A over here, okay, which has gas particle, right? Let's say these are gas particles. Then we have container B, right? So we have increased the temperature. We have increased the temperature, right? And but we have basically we want to basically make sure that the pressure remains constant, right? So now what is happening over here? Okay, we have the same number of particles that are five, three, six particles over here, right? So what has increased, right? So in spite of heating it up, I want to make sure that the pressure exerted, that is basically the collisions, the rate of collisions, right? The collisions with the walls and with the container are basically reduced, right? So that I can basically decrease this, right? If I decrease this, I will have the same amount of force that was actually applied in container A before the temperature was increased, right? If you find this part to be confusing, you can go back and rewatch this statement, right? If you have further queries, you can basically text on the WhatsApp group, okay? So if I increase the volume of the container, right? Let's say now this is gas B. So I have the same number of particles, right? But it is occupying more space right now, okay? So now I basically increase the temperature. So what has basically been shown over here to make sure that my pressure remains constant, right? So if my temperature will increase, so does my volume would increase, right? Just to make sure that this rule is getting satisfied, that my pressure should be constant, right? So this thing basically gives us the following relation, that volume is directly proportional to temperature, right? If I increase the temperature, okay, so should my volume of the gas should be, right? It makes sense, right? You can just basically take a balloon and fill it up, right? And if you try to heat it up, okay, let's say, if we, let's say, talk about the hot air balloon, right? So what do we do? We have the air, right? The hot air balloon has actual air, which is the air which we breathe. When we basically heat up the gas at the bottom of the hot air balloon, the gas basically expands, right? It expands and basically causes the balloon to inflate, right? So that basically causes what? If you increase the temperature, the volume of that actual gas which was surrounding the balloon basically increased and caused the balloon, hot air balloon, to expand, and basically it can basically now float, right? So yeah, and since V density equals to mass upon volume, if you increase the volume, the density decreases. So your basically hot air balloon goes up, right? So this is the relation which basically we'll discover soon, right? And this is the experiment, okay, which will basically uh back up the derivation which we will do in the next slide, right? So we have the following relation again with temperature and volume. And this is temperature, let's say in Kelvin, and this is basically pressure in Pascal, right? Sorry, not pressure, it's volume. It's volume in meter cube, right? So it's a direct relation. So it should go like this, right? So if you increase the temperature, so should your volume should increase, right? So it's a direct proportional relation, that volume is proportional to temperature, right? Okay, I hope it makes sense. Now we have the final experiment, which will basically use to derive the following equations, which will be coming in the next slide. So what is the experiment over here? We have a constant temperature, right? So we're not varying the temperature of the gas, okay, or the liquid which we have in the experiment. So let's see what is the book saying. So if the volume of a fixed mass of a gas, right, mass is same, right? The mass is fixed. So we're trying to relate pressure and volume, right? So pressure can be changed by using a piston over here, right? Okay, which are gray colored over here. So what is happening over here? They are saying that the actual basically gas, the original gas had volume V, right? So how do you find volume? Basically find a cross-sectional area. You can multiply with the height h, right? So volume is basically area into h, right? So the volume occupied by the gas is actually V, okay, when the pressure is P, right? So now in this second case, you basically increase the pressure to twice, 2 times P, right? So what is the relation of this now? Your volume basically became now what? Half, right? So this piston went down to a height of h by 2. The cross-sectional area is same, right? So now the volume is basically what? It's V bar is now V by 2, right? So the relation is basically, now you can find it out over here, that the pressure is doubled, the volume has basically halved, right? So the relation with the pressure and the volume is as follows, that pressure is inversely proportional to volume, right? I hope it makes sense to you guys also, right? So if I wanted to try relate this on a graph, let's say you have volume in meter cube, right, and you have pressure in pascals. So the relation is as follows, right? It is an inverse relation over here, it goes like this. So if you basically increase the volume, pressure should basically decrease, and if you want to increase the pressure, okay, so your volume would decrease, right? Okay, this is the relation over here. I hope it makes sense. These are simple experiments just to basically back up the derivation which we will be doing in the next slides, right? So you can just pause it over here. You can basically rewatch this part also. Okay, if you're confused, you note down queries in a copy, right, and send it as a PDF on the WhatsApp group. Okay, if everything is clear, we are good to go. So let's proceed over here, right? So we have now some numericals over here, right? Some derivations and then numericals over here. Going to be pretty simple over here. Okay, so don't worry. If you have any questions, please mark it out on a piece of copy or on your tablet. Okay, just make a PDF and share it in the WhatsApp group. Okay. So again, Boyle's law, right? So now what is a Boyle's law? We had done this already in the last slide over here. It basically relates pressure and volume, right? So we have seen the relation in the last slide, that pressure is inversely proportional to volume, right? So if you want to basically remove this sign of proportionality, you basically introduce a constant over here, right? So this is going to be P equals to some constant, let's say K, okay? upon V, right? So where K is what? K is a constant, right? It is any number over here. It can be 1, 2, 3, 4, 5, any number, right? It can be 0.1 also, 0.2 also. Okay. It belongs to real number, right? So what are real numbers? You search it on internet. Okay. These are all the numbers which you have, right? Okay. Real numbers. Okay. These are real numbers over here. Okay. So now if I want to make K constant over here, what will I get? I get K equals to basically P times V, right? So let's say if I have multiple cases, let's say I have the same gas, right? But I'm varying the pressures, right? Like over here. Let's say I have the same gas over here. I'm just basically changing the position of piston to basically if change the pressure, right? So I can relate this thing as follows, right? This was let's say P1, right? And it had a volume 1, right? It had volume 1, V1. So now the pressure is basically P2 on the piston and the volume occupied by the gas is now V2, right? So I can now relate these two things as follows. That is P1 V1 equals to P2 V2. That is saying K, if you have the same gas, if you multiply P1 V1, that will give you constant K, let's say. Okay. Now let's say if you multiply P2 V2, your you will also have a constant K. So that K is same, right? Because of this Boyle's law. Okay. Keeping that in mind, you have the same gas. So you can also relate this thing if you have two gases like this. Let me just copy the picture again. Okay. Let me copy it here and let me take it here. Let me insert a slide. Okay. Blank slide. So if you have this case over here, so what is it stating, right? So we have V1 here, and this piston is exerting a pressure of P1, and this pressure is changed to P2, and it occupies the pressure of P2, right? So if I use Boyle's law twice, what will it give me? Okay, P1 is basically equals to some K constant upon V1, right? So if I apply the Boyle's law over here, so this will also give me another pressure that is P2 equals to K upon V2, right? The K is constant because the gas is same, right? The gas is same over here. We have kept the temperature to be constant. So we can equate basically the K, right? So K equals to K. So this thing basically becomes what? This becomes K equals to P1 V1. And this equation becomes what? This becomes K equals to P2 V2, right? So you can equate, let's say this is equation A, and because this is equation B, you can equate both the equations, equation A equals to equation B, right? So you will have therefore the following relation that P1 V1 equals to P2 V2, right? So if you have, let's say, you have a question in the next slide that will basically explain that how it used, right? Therefore shown. This is a mathematical symbol which means basically shown, right? Okay. So now let's go and solve a question, right? So let's apply this over here, right? So you have the following question over here that certain quantity of gas has a volume of 40 centimeter cube when the pressure was 1.5 pascals. You want to find its volume, that is V2. Now when the pressure is changed to 2.5 pascals, you are given that the temperature remains constant, right? So again, let me copy the diagram over here. This is a very good example just to basically understand the application of the formula. How do we apply this formula, right? So given the P1 over here, right? So the pressure 1 of the piston that is given to you as the P1 is 1x.5 pascals, right? And then when the piston is changed to a different height, okay, the piston applies a pressure of 2x.5 pascals, right? So initially the volume V1 that is given to you that is occupied by the gas in this container is 40 centimeter cube, right? Okay. So you want to basically find out the volume in volume 2, right? What is the volume 2 over here? So you can simply use the Boyle's law, right? You can just write and I'm using Boyle's law over here. Boyle's law. And what does it say? It says the following thing. Okay. First of all, if you don't have the diagram, you can write down the data as follows. That what is given to you? Given that P1 is 1x.5 pascals. If you recall, this is the atmospheric pressure, right? And if you basically then you have V1 that is 40 centimeter cube. We convert this into meter cube as follows, that 40 into 10 to the power minus 6, right? Meter cube. Okay. So, and you're given also P2. So your P2 is basically 2 exponent 5. Okay, it's 2 exponent 5 pascals. And you want to find basically what? V2 is what, right? This is how you can write down the data over here. Okay. Okay, so this is how you can write down the data over here. So let's apply the formula and let's find it out, right? Okay. So is this P1, V1 equals to P2, V2, right? Just put in the values and get your answer. It's 1 exponent 5 into basically 40 exponent minus 6. And the V2, P2 is basically what? It is 2 exponent 5 into X, right? So your V2 is X, right? X meter cube. Okay. Okay. So now this is basically your question. You can just use a calculator to get the answer, right? Okay, so just solve it out. So your V2 is going to be what? It's going to be 1 exponent 5. If you find any mistake in the solution, you can just take a screenshot. I can just label it there, right? Okay, so you did this calculation error, right? I also am a human being. I might make a mistake also. Okay, I believe there is no mistake in the conversion, right? It's fine, right? Okay, so divide by 2 exponent 5, right? So this is going to give you V2, and your V2 is going to be what? Your V2 is going to be as follows. That is going to be, okay, so it's going to be 1 exponent 5 into 40 exponent minus 6, right? Divided by 2 exponent 5, right? So your volume is coming out to be 20 micro, right? It's coming out to be 20 micrometer cube, right? That is basically, macro means 10 to the power minus 6, right? So your V2 is coming out to be 20 exponent minus 6 meter cube, and it makes sense, right? So initially your volume was 40 micrometer, right? Now it has basically went to half, which makes sense, right? So what has happened over here? So yeah, over here P2 is 2 times P1, right? So logically the V2 should be half of V1. Okay, it should be 20 centimeter cube. So this is the exact thing which you're getting over here, that is 20 centimeter cube, right? Okay, so it is a meter cube. In just convert this, it is going to be same, right? Okay, so convert this into a centimeter cube. That can be a homework segment, right? So convert this into centimeter cube, right? This is your homework. Okay, this is your homework assignment. Homework. Let me just label it also clearly so that you cannot forget this. Okay. So yeah, so now we are done with this. So now proceeding towards the very last derivations, then we will end the lecture, right? And you will have another session, basically lecture for the question answers. We have your test tomorrow, right? That is Monday. Okay, so be prepared for that and make sure to watch all the lectures before the exam. The exam is going to be simple. It will contain two sections, MCQ and theory, right? It will be 1 hour, and Sman would be there to basically monitor you guys. Okay, so I'll be traveling, I'll be in the flight. I might not be able to basically get online. Okay, so now we have Celsius and Kelvin scales over here, right? This is basically pretty simple and straightforward. So at room temperature, right, at basically at constant air atmospheric pressure, right? So you have the following axis over here, right? So this is temperature scale over here and volume of pressure, right? So this is basically the zero crossing, right? So 0 Celsius basically corresponds to what? It is 273 Kelvin, right? And I recall that I have told you guys what is absolute zero. Absolute zero is the lowest temperature that has been that is possible in the universe, right? So absolute zero is basically called 0 Kelvin, right? So it is the lowest point which we can hit in the temperature, right? So at this point, the particle that matter are most stops to move, right? So if you basically try to relate, so your 0 Kelvin is basically negative 273 Kelvin, right? So if you try to map it out on a graph, it should look like this. So you have volume of pressure of the gas, on the y-axis, and then you have temperature on the x-axis, right? So at 0 degrees Celsius, there would be some volume, right? That means that there would be some spaces between, let's say ice cube, right? And ice cube. So solid would have some small spacing between the particle, right? So, and they would be vibrating by remaining in the fixed position, right? So if I reach at the absolute zero, which is this particular point, right? So this is basically this particular point. Okay, so now if we basically reach this particular point, which is called the absolute zero. So what is absolute zero? In this particle have zero motion and the volume theoretically basically goes to zero, right? So that means that you can shrink everything into a dot, right? So that means that all the particles squashed up together and all the minute spaces are reduced. Okay. So that basically reaches the absolute zero temperature, and at this temperature, there is no particle movement, and that is theoretically possible. Right? So there might be some kelvins at zero, there might be some Celsius, because there might be some slight movements, but theoretically it should be basically no particle movement should be there, right? So this is basically the relation of Kelvin and Celsius, right? So we have a equation which can relate these basically two things, which is as follows. So if you want to find temperature in Celsius or temperature in Kelvin, that is going to be temperature in degree Celsius plus 273, right? So for your basically reference, the actual value is basically 273.15. Okay, but we in O levels, it is out of 273, right? So yeah. So let's say this is the relation basically between Kelvin and Celsius. Let's say if we have temperature in Celsius to be 0 degrees Celsius, right? So in Kelvin, if you want to find it out, just use this equation. So temperature in Kelvin would be it's 0 plus 273. So it's going to be 273 Kelvin, right? Okay. So you can also this book has used a variable that is theta. So theta basically shows what temperature in degree Celsius, right? I hope it makes sense. Okay. So this is the next slide, which is the same which I have explained right now, right? So 0 Celsius means 0 to 73 Kelvin. So if you 15 Celsius, you have a relation, right? That is this equation. Just use this equation to find out the different temperatures of Kelvin. Okay, when given the Celsius temperature over here, right? Okay, so again, the temperature T is for Kelvin over here. So T is giving you temperature in basically Kelvin, right? And the theta is giving you temperature in Celsius, right? Celsius. Okay. So this is the same question which we have used, and you just want to now solve the question. Right? Now you can pause the video here, try to solve the question on your own, and then play it again. Okay? So I'm going to solve it fast. You can just pause the video whenever there's a question, solve it on your own. You can using a pencil, a copy, and your obviously and calculator. But if you're smart enough, you think, okay, I can do it manually. Okay, or let's say on your own mind, right? If your mental math is pretty strong, you can do it on your own also. Okay. So now what is given to you? What is given to you over here? You're given the temperature in degrees Celsius, right? That is 27 degrees Celsius. You want to find what? You want to find the temperature, this value in Kelvin, right? Okay. So you have a relation that is as follows. The temperature in Kelvin equals to temperature in Celsius plus 273, right? Plus 273. So just put in the values and get your answer. So temperature in Kelvin is equals to basically 27 plus 273, and that gives you a value of 300 Kelvin, right? I hope it makes sense. It's pretty simple and straightforward, right? That is your answer. Now we have the part B over here. Again, pause the video, solve it out, and then play it out. Okay. Now you're given the opposite things over here, right? Now you're given what? You're given the temperature in Kelvin. Okay. That is 60 Kelvin. And now you want to basically find out the temperature in Celsius. That is degree Celsius, right? That is going to be unknown. So again, you have a relation. So writing the equation in is basically gives you 1 mark, right? So temperature in Kelvin is equals to temperature in Celsius plus 273, right? So again, put in the thing which you know, that is 60 equals to x plus 273 TKD, and therefore if you make x subject, this goes over there and subtracts. So x is basically 60 minus 273, that gives you a negative 213 Kelvin, right? Okay. So that, sorry, not Kelvin, Celsius. So that means you cannot live in this area, right? Let's say if you're living in this particular country or city or let's say planet, life is not possible because the cells, the normal cells in which the life is possible is basically around 37 degrees Celsius, right? So if the temperature drops below this, uh, enzymes or let's say life cells dies, right? Achari. So now I hope that this is clear till now. Let's move on to the last relations. That is charge law, right? So we have seen the relation before that how does volume and temperature relates. That is volume and temperature relates linearly, right? That they are directly proportional to each other. That if you increase the temperature, so does your basically volume. Okay? So this is called the charge law. And if you guess it right, then congratulations, you basically remember the formula, right? So it just basically say that volume is directly proportional to temperature. If you want to remove the sign of proportionality, you basically introduce a constant that is V equals to let's say K times T, right? So again, K is over here what? K is a constant and this constant can be anything, any number that which basically belongs to real number, right? Okay. So now if you want to make K subject, so K comes out to be what? V upon T, right? So this is the relation over here, right? Okay. Let's say if you have again the same case which you basically saw with the last slide. Okay. So let me just fix it. Let's say if you have now, this is the relation over here, hence shown, right? So you can also equate the two constant. Let's say if you have two temperature value given to you and one volume given to you, and you want to find the other volume at temperature. Let's say you're given V1, T1, and of the same gas, and you're basically given a V2, okay, and you have T2. Let's say your T2 is unknown, right? Your T2 is unknown, okay. So you can equate the constants and you will get the following relation, right? So you will get the following relation that is V1 upon T1 equals to V2 upon T2. You can just put in the value which you know and you can find out the unknown, right? So that's how you can utilize the formula if you have the two scenarios for different for same gas over here, right? Then we have the pressure law, right? We have also seen this in the last like example which we basically taught in detail in this basic experiments, that how does pressure and temperature relates, right? So pressure and temperature again relates directly proportionally, and this basically again follows volume and temperature. That is, they are directly proportional to each other, right? So let me just do it over here. So again, the pressure is directly proportional to temperature, okay? And if you want to remove the sign of proportionality, you basically reduce a constant, right? And I'm naming the constant to be k, and k is a constant which basically includes any numbers which belongs to real number, right? Any real number, right? Okay. And let's basically introduce a constant over here. It becomes kt, right? Let's make k subject. So k becomes p upon t, right? And let's imagine you have again, let's say p1, t1, and if you're given also T2, T2, right? And let's say this time your P2 is unknown, right? And you're given P1, T1, and T2. You can again equate the constants since the gas is same. If the gas is same, you can apply this formula over here. That becomes P1 upon T1 equals to P2 upon T2. Then you can again put in the known variables and you can just find out the unknown variable over here, right? This is another variation over here, right? This is another variation, right? So hence shown, right? Hence shown, right? So I hope it makes sense. This is again just converting the experiments into equation, right? This is not so difficult. If you have questions, feel free to share them on the WhatsApp group, right? Then how can you combine all of these laws, right? Now the combined law becomes as follows, right? We have seen this that pressure was inversely proportional to volume, and pressure was basically directly proportional to temperature, right? And if you basically introduce constant in, let's say, equation A and equation B, what does it becomes? The equation A becomes as follows, that PV equals to constant, right? And P upon T equals to some constant, right? Right? So basically the pressure, if you combine all of this together, okay, so the formula, the combined version of this becomes as follows, right? Combined version of this basically equation becomes as follows. That is PV upon T equals to constant, right? And you can just feel this relation, right? You can just feel this relation and you can also make sense of it, that PV makes sense, right? If you send V over there, P and V are inversely linked together, right? And if you relate P and T, it becomes directly linked together, right? So the combined law is as follows. Let's say if we have for cases when we have basically P, V, T for all change from, let's say it was initially P1, V1, T1, it changed to P2, V2, T2. So you can basically apply this combined equation and basically find out the unknown variable, right? Let's say this was unknown T2, you can find T2, right? So this is basically another version of the combined laws, right? Of the combined law, right? This is the combined law, right? This is the combined law. And what is it combining? By the way, think about it. It is basically combining the Boyle's law, right? It is combining the Boyle's law and the Charles law, right? So what was the basically Boyle's law? The Boyle's law was basically pressure is inversely proportional to volume. And what was the Charles law? Okay, that volume is directly proportional to temperature, right? So either way is fine. Okay, or you can also say it is also combining pressure law, right? Pressure law क्या था? Pressure law was basically saying कि pressure is proportional to temperature, right? And this is another version of the combined law, right? This is pretty simple. And for exercising over here, for just practicing over here, this is your homework. And I need the summation of this PDF by basically tomorrow's afternoon, right? That is 12 p.m. Okay, 12